many R's are in the word strawberry? Ask most AI models, and they will confidently say 2. But the answer is 3. This is not a thinking error. This is a seeing error. Watch what happens when we look at strawberry the way the model does. It never sees 10 letters. It sees 3 chunks, STR, AW, and berry, each assigned a number. 496, 675, 15,717. The 3 R's? Scattered across separate chunks. The model cannot look inside any of them. So if the model is blind to letters, what does it actually see? That is what we are going to uncover. To uncover this, we need one basic fact. Neural networks do not understand text. They work with numbers. Every word you have ever typed into GPT, Claude, or Llama first passes through a process called tokenization. The tokenizer chops your text into pieces, gives each piece an integer, and those integers are all the model ever receives. How you chop up the text turns out to matter enormously, and that decision changes everything. Let us try the obvious approach. Give every word its own number. The is 1. Unbreakable is 2. Chatbot is 3. Simple enough. But English has over 170,000 words in common use. Add technical terms, slang, and misspellings, and the vocabulary explodes past 500,000. And when the model encounters a word it has never seen, a brand name, a foreign phrase, it is completely stuck. That word becomes unknown, and the model is blind to it. So what about the other extreme? Give every character its own number. The vocabulary shrinks to about 100 entries, and you can represent any text. But look what happens. A 3-word sentence becomes 23 individual tokens. A full paragraph becomes 2,500 tokens. Transformer attention scales with the square of sequence length. So this is computationally devastating, and each character by itself carries almost no meaning. Is there a middle ground? What if we found useful pieces somewhere in between? That is exactly what subword tokenization does. Keep common words like the as single tokens, but break rare words into meaningful pieces. Unbreakable becomes unbreakable, 3 known pieces that compose into any word. The vocabulary stays manageable, sequences stay short, and nothing is ever unknown. Every major language model, GPT, Claude, Llama, uses this approach. But how does the tokenizer figure out which pieces to use? It does not have a dictionary of prefixes and suffixes. It discovers them automatically, using a beautifully simple algorithm called byte pair encoding. The algorithm is called byte pair encoding, or BPE. It was invented in 1994 as a data compression method, and today it powers the tokenizers behind GPT, Llama, and Claude. Here is how it works. We start with a tiny corpus, the cat in the hat. We split every word into individual characters and note how often each word appears. The shows up twice, the others once each. Our starting vocabulary is just 7 characters: T, H, E, C, A, I, and N. Now we do something clever. We scan the text and count every pair of characters that sit next to each other. T next to H appears twice, because the occurs twice. H next to E also appears twice. A next to T appears twice as well, once from cat and once from hat. The remaining pairs each appear just once. 3 pairs are tied at a count of 2. BPE picks 1. Let us merge T and H into a new token, TH. Watch what happens. In both copies of the T and H boxes slide together into a single TH box. Our vocabulary grows from 7 to 8 tokens. Now, we recount the pairs with our updated vocabulary. TH next to E has a count of 2. A next to T still has a count of 2. We merge A and T into at. Notice something interesting. Both cat and hat now share this new at token. The algorithm discovered a common word ending without being told anything about language. One more merge. TH next to E appears twice. We merge them into the. And just like that, after only 3 merges, THE, the most common word in English, became a single token. Cat is now just C and at. Hat is H and at. Our vocabulary grew from 7 base characters to 10 tokens. Take a moment to appreciate what just happened. A simple rule, merge the most frequent pair, automatically discovered useful word pieces from raw text. No dictionary, no grammar rules, just counting. In a real tokenizer, this process continues for thousands of merges. GPT-2 applies 50,000 merge operations, building 50,257 tokens from 256 base bytes. But the principle is identical. Count pairs, merge the winner, repeat. We said GPT-2 starts from 256 base bytes, not characters. Why? A character-level tokenizer only knows the characters in its training data. When it encounters a Chinese character, an Arabic letter, or an emoji it has never seen, it is stuck. That character becomes unknown. GPT-2 solved this by working with raw bytes instead. Every piece of text in any language is stored as bytes. The standard UTF-8 converts characters into 1 to 4 bytes. An English letter takes 1 byte, an Arabic letter, 2, a Chinese character, 3, an emoji, 4. There are exactly 256 possible byte values, so the base vocabulary is always 256 tokens. BPE merges build on top of this foundation, just like before. And because any text can be broken into bytes, the tokenizer never needs an unknown token. GPT-2's vocabulary, 256 bytes plus 50,000 merges plus 1 special token. 50,257 total. But notice, a Chinese character starts as 3 bytes while an English letter is just 1, a 3 times disadvantage before BPE even begins. If the training data is mostly English, English patterns get far more merges and better compression. Non-English text stays fragmented. Now, let us trace the full journey from your keyboard into the transformer. Now let us put the whole journey together. When you type the cat sat, the first thing that happens is pre-tokenization. A pattern splits your text by character category, keeping letters, numbers, and punctuation separate. This prevents things like dog and the period after it from becoming 1 token. Next comes BPE segmentation. The merge rules from training are applied in the exact order they were learned. The passes through as a single token. Cat becomes C and at. Then each token maps to its integer ID. And here is the crucial step. Each ID looks up a row in a massive table called the embedding matrix. Each row is a dense vector, a list of hundreds of numbers that captures the learned meaning of that token. For GPT-2, this matrix has 50,257 rows, each 768 numbers long. That is 38.6 million parameters just for this one table. These vectors, with positional information added, are what the transformer actually processes. Everything the model knows about your text flows through this pipeline. There is no other way in, and that is exactly why the consequences of tokenization reach so far. Now let us see what this pipeline causes in the real world. Take artificial intelligence. In English, that is 2 to 3 tokens. In Hindi, the same concept needs 10 to 15. A Hindi speaker pays 5 times more per API call, fills the context window 5 times faster, and gets measurably lower accuracy. Research found tokenization lengths up to 15 times longer for the worst affected languages. Numbers break too. 127 becomes 1 token, but 677 splits into 2. When adding 1, 2, 3, 4 plus 5, 6, 7, 8, a human aligns digit columns. But the tokenizer creates 12 and 34, 56 and 78. The boundaries slice across digit positions. Column-by-column addition is impossible when the columns are shattered. Letters, numbers, languages, all the same root cause. The token is opaque, and the model cannot see inside it. The industry knows this matters. Vocabulary sizes have quadrupled in 6 years, from GPT-2's 50,000 to GPT-4o's 200,000. Bigger vocabularies help, especially for non-English text. But they come with costs, hundreds of millions of extra embedding parameters, and they do not fully solve the fairness problem. Several common beliefs about tokenization also turn out to be wrong. Before we wrap up, let us bust 4 common myths about tokenization. Myth 1. LLMs see individual characters. No. Models see opaque token IDs. Strawberry is not 10 letters to the model. It is 3 numbers, 496, 675, 15,717. It has no access to the characters inside. Myth 2. Tokens are words. Not quite. Tokens are frequently subwords. The word tokenization itself splits into 2 tokens. English averages about 1.3 tokens per word. Myth 3. Tokenization is just pre-processing, a boring step before the real work. Wrong. It is an architectural decision as important as model size. It determines what patterns the model can learn and where it will fail. Myth 4. A bigger vocabulary is always better. Not so fast. A vocabulary of 128,000 tokens needs over 500 million embedding parameters, and diminishing returns appear beyond about 100,000 tokens. Now, let us step back and see the full picture. Every piece of text that enters a language model passes through this pipeline. The tokenizer sits at the front, and every decision it makes cascades through every layer that follows. This is not pre-processing. This is architecture. The model that could not count R's in strawberry? Blind from the start. The model struggling with addition? Its tokens shatter the digit columns. 5 times more expensive in Hindi? The tokenizer was trained on English data. Every one of those failures traces back to this invisible step between your words and the model's numbers. Now you can see it. Next time an LLM does something strange, do not ask what it was thinking. Ask what it was seeing.